Okay, are we ready to go?
Yeah, I think so.
Okay, great. Well, good afternoon, everyone. Thanks for joining today. So this is the fourth in our series of hub webinars. Today's presentation is on multifunctional structural composites by Emil Greenhalgh from Imperial College. Before Emil gives his presentation, I'll give you a quick overview of the hub, reflecting on its current status as we approach the 7/10 milestone. And the video today will be on the on our website, simcomp.ac.uk. Now, could I ask you, if you have any questions, could you send them in via the box on the screen, and we'll deal with them at the end of the presentation. So thanks very much. So the hub's a significant investment in composites manufacturing research by the EPSRC. It's 10.3 million over 7 years. And the four objectives for the hub are, firstly, to deliver research excellence in composites manufacturing. Secondly, to deliver these research findings to industry via the high-value manufacturing catapult center network. Third, to train early career researchers in PhDs, NGDs, and postdoc work. The NGDs are trained via the EPSRC Center for Doctoral Training in Composites Manufacturing at the University of Bristol. And fourth, to build national and international networks and to develop collaborative research programs. So to date, we have 15 academic partners who've collaborated in research projects in the first half of the hub. And we have 37 industrial partners and 4 catapult center partners, and we're very grateful for their support. So we've funded 29 projects so far, including 6 core projects, 4 fellowships, and 19 feasibility studies. We've just approved 5 more feasibility studies, and 2 more fellowships are out for review. In addition, there are 28 leveraged PhDs and 39 NGDs. The projects are all within our research theme framework, where a project can be in theme 1, high rate deposition and rapid processing. Theme 2, design for manufacture via validated simulation. Theme 3, multifunctional composites and integrated structures. Theme 4, inspection and in-process evaluation. And theme 5, recycling and reuse. To maximize the synergy between projects, to ensure the sharing of best practice and to avoid repetition, we're using a workstream project management approach. Each workstream is a particular technology and is led by a national leader in the area. All projects are connected to a workstream, and the workstreams feed into the research themes. So you'll see quite a lot of interaction across the portfolio. In today's webinar, we're looking at the research highlights from workstream 3, multifunctional structural composites. So the DAISY diagram here shows how the projects in workstream 3 are connected. So the multifunctional core project at the center is linked to 2 other core projects in dark blue and to 5 feasibility studies in light blue. 7 industrial partners in orange are associated with this workstream, and industry and host institution contributions provide the PhD and NGD student funding. So the images on the right show some of the work that Imperial and Bristol have undertaken within the hub to create 3D structures from the 2D supercapacitor laminates. And I'd like to thank you all of the hub partners, the industrial partners and the academic partners and staff, and to Fluency Marketing, the hub dissemination partner. And without further ado, I'd like to introduce you to Professor Emil Greenhalgh in his presentation today, Manufacturing for Structural Applications of Multifunctional Composites.
Great.
Thanks very much.
Great, thank you, Nick. I'll just share my slides. Okay, so you should all be seeing the design and manufacturing issues for multifunctional structural composites. So thank you very much for giving me the opportunity to give a presentation on the work we've been doing. I'm going to spend about 45 minutes running through the work we've been doing on development of structural power materials and multifunctional structural composites, but with a particular focus on the design and manufacturing issues. So let me just run through the structure of the talk. So I'm going to first introduce what are multifunctional structural composites, and then talk a bit about the motivations for structural power. What's the reason that we've sort of developed this area? And then we'll move on to giving an overview of the state of the art. So I partition that into the constituents and the devices, the modeling work, and scale up and demonstration. I'll then focus on multifunctional design methodology and manufacture of multifunctional devices. And then I want to just sort of touch on some of the other work that's been going on within the theme 3 of the hub on multifunctional materials. And then I'm going to close the presentation by talking about where these materials could be adopted and the outlook for these materials. But let me first of all introduce you to the team. So I lead the group on structural power materials at Imperial, and I have 2 academics who work with me. Professor Kirsenak, who is an electrochemist and brings that expertise, and Professor Schaffer, who is focused on nanomaterials, and particularly nanocarbons. And this is one of the challenges in working on materials like these, is that you're having to bring in very diverse capabilities. There's no one person that's an expert in all the capabilities you need to have. Electrochemistry, composite mechanics, and I think this is actually quite a challenge for training people in this field, is that it's difficult for people to have that diversity of skills. So we have a number of postdocs that are covering areas such as the material development, current collection, device manufacture, going up to sort of assembly and design. We have a number of PhD students that have been working on areas associated with this, and there's a couple more academics that have been involved in the work that we've been doing. And so this is the Imperial team, but we're also collaborating across the world in this area. And as I'll show you, a lot of the effort in this area is going on in Sweden. Leif Asp's group at Chalmers and Dan Zenkert's group at KTH in Sweden have really been focusing on structural batteries and doing a lot of the development work of the constituents there. Natasha Sheshova's done some excellent work on the development of the structural electrolytes, and she's been working in this area for quite a while. And through the hub, we've been working very closely with Dimitri's group, particularly looking at the manufacturing issues, and I'm going to flag up some of the work they've been doing within the hub as well. So let me introduce what multifunctional structural materials are. So these are materials that are structural materials. They look like bits of carbon fiber, but we've also imbued them with additional, often disparate functions. So structural batteries, let me just switch to the laser pointer. So we have structural batteries, for instance, but you could look at energy harvesting, actuation, self-healing, sensing. So these are structural materials, but they can do other things as well. And the nice thing about this class of materials is that the application is very broad, but I think it's particularly useful for transport applications. So I wanted to just emphasize that we're not focusing on smart structures here. So the approach to design in engineering traditionally is to compartmentalize. You'll have a part of a platform which is the load-bearing, mechanically load-bearing part. You'll have a part of the platform that stores the energy. And so you often, from a conventional engineering point of view, have compromises where you're trying to optimize the design for mass or volume or cost. So we're taking a much more holistic approach. So in the field of multifunctional materials, multifunctional structures, you can partition it into 2 classes. There's this idea of multifunctional structures where we take a sensor or a battery and we embed that within a composite structure. And so there's some really good work that's been done for several decades by the group at the US Navy, Jim Thomas, where they've been embedding batteries into composite structures and have made these drones, which have actually been used in service. What we're doing is not that. We're actually trying to take a material and imbue it with 2 functions, a structural function and an additional function, in this case energy storage, simultaneously. So you don't have monofunctional assemblies that bring together a multifunctional structure. You have a multifunctional material. So for instance, in the work in Sweden, they're taking conventional carbon fibers and they're not only carrying mechanical load in those, they're allowing lithium to intercalate into those to act as a battery. So let me sort of talk about the motivation for what we're doing and really put this in the perspective of dealing with sustainability and the climate emergency. So there's a really big drive to go for electrification of transport. So one of the problems here is that To get the range that we want, for a car, for instance, we need to add more batteries, but that battery adds more mass to the vehicle, so you then need to have more batteries to go even further. So this spiral means that you're ending up with cars which have 25% of the weight of the car is actually the battery. Aerospace, it's even worse. If we've got this aspiration to have a long-haul passenger jet by 2050, then we've got to look at how we replace aviation fuel. So typically, for a civil airliner, you're looking at about 30 kilograms of kerosene per passenger. With current batteries of today, you'd need 1,000 kilograms of batteries per passenger. So that's clearly not feasible. So the electrochemistry community, the approach they're taking is to really try and enhance how much energy the batteries can store. But that's giving real issues with the sustainability, longevity of the batteries, and safety. And we all have heard about the Boeing 787 fires, for instance. So there really is a different approach needed to how we store energy. And so this really gives us the motivation for the idea of structural power. So these are structural composites which store and deliver electrical energy. So this, for example, is one of our devices. It looks like a conventional carbon fiber composite, but it stores electrical energy. And so this is why we've come up with the term massless energy. And this is a completely different way of using structural materials. It's not really been tried this way before. So let me talk about my vision for structural power. So as with any new technology, it's looking at huge mass and volume reductions. And we've recognized that this is something that it's going to offer. But we can see more than this with the idea of structural power. We've seen that a lot of devices like your mobile phone, the thickness of that is really dictated by the size of the battery, the thickness of the battery. But if we can now dispense with the battery, we make the casing out of the phone out of something that stores electrical energy, then you can look at making phones much more slender. You can have phones as thin as credit cards, perhaps. And this concept of slenderization is something that we've recognized with structural power. From an aerospace perspective, there's a really nice thing happening here that currently we store fuel or maybe batteries in the wings of aircraft. But if we could make the structure of the wings out of a material that stores energy, then the wings could be very slender. And that gets my colleagues in the aeronautics department very excited because that's going to reduce drag, greatly increase range. But it means aircraft will look completely different, as the sort of configuration shown here. We'll have new places to store energy. So perhaps, for instance, making the pylons of wind turbines out of our material so you can store the energy from wind turbines locally. And this is something, again, we've picked up with structural power, that it's actually going to promote the idea of localization of energy storage. And we see the cabin as a really good area that we could start to adopt this technology. So at the moment, to drive the seat back displays in your aircraft cabin, that drains energy off the engine. So there's a lot of wiring associated with that. But if you can make the seat out of our material and deliver the energy to power the entertainment units, the USB chargers, everything is local, and you massively reduce wiring. We also, in the longer term, start to see this idea of batteryless devices. So things that we've never thought about putting batteries in because of the sort of thickness that it imparts, we could start to do with structural power. And then from an engineering perspective, this is a really innovative way to use materials. You're using materials to do two things simultaneously, and we don't really have an engineering framework of how to design with these materials. So this is something that we've started to work on, and I'll talk about a little later on, is how you use a material and design with a material that does two things simultaneously. And in the longer term, well, we think this is the end of conventional batteries, that you won't go to the shop and buy battery packs such as these anymore. You will have a structure that doubles as an energy storage medium. So let me move to some of the concepts for structural power. And as I said before, there's work on batteries, and we can look at a fiber level battery here that the suite have developed, and also a laminated type of construction of battery. And what we've been focusing on at Imperial has been structural supercapacitors. So these store less energy than a conventional battery, but they deliver energy much more quickly. And there's similar work going on in Spain, for instance, but using carbon nanotubes as the electrodes for those materials. So let me talk a bit about the state of the art with these materials. So just to explain our architecture, you have some electrodes, which we're using carbon fiber spread tow, which is infused with a carbon aerogel. So that's a sort of nanoscale foam. You attach current collectors to those to help you deliver the energy off the device. You have an electrolyte, which is a combination of ionic liquid and epoxy. And you have a separator, which basically stops the electrodes from touching each other. But that separator needs to be thin because it's got to allow the ions to move across that interface. So let me focus on those constituents. And first of all, the reinforcement. So that's the reinforcement. It's also the electrode. So what we need for our devices is to have a very high surface area. And the problem with carbon fibers is they only have a surface area of about 0.2 meters squared per gram. We need to have tens, hundreds of meters squared per gram to give us a high energy storage. So we've been exploring the route of using carbon aerogels to do that. These are effectively a nanoscale foam which we infuse between the fibers and fills the matrix space between the fibers. And that aerogel then gives us the huge surface area, but it also gives us some benefits from a mechanical perspective as well, because it's stiffer than conventional matrix. And then we're able to add additional materials to that aerogel to improve its energy storage capacity. So it acts more like a battery. We found that the carbon aerogel bonds really well to the carbon fiber. So this micrograph is showing you a carbon fiber, and this is the aerogel. You can see it's a very granular nanoscale foam. However, we found that there's something going on with the cagging process, the carbon aerogel process, which seems to be damaging the carbon fibers. And that's something that we're still trying to get to the bottom of. Then the electrolyte, which I think is probably the most challenging part of this whole area, is developing a matrix material that stores electrical energy, or sorry, allows ionic conduction and is rigid enough to apply mechanical loads. And so this is the work that Dr. Shof has been working on at Durham. And she's recently had a paper that's been explaining the work that she's been doing. The approach we've taken has been mix a structural epoxy with something called ionic liquid. So this is a material that's used in conventional supercapacitors and batteries as an ionic conductive material. And by manipulating the weighting of the structural phase and the ionic phase, you can get a range of properties as illustrated here. So again, this is an area that Natasha's group have got really good control over the microstructure. But one of the problems we've encountered, and this really feeds into the manufacturing issue, is that when we have that well-controlled microstructure that we introduce the fibers to, that microstructure becomes non-optimal. We get heterogeneity developing. So we start to see instances of the carbon fibers being sheathed by the structural phase of the electrolyte. So that's going to be good from a mechanical perspective, but it doesn't allow ionic access. So it reduces electrochemical performance. And we also have seen heterogeneity of the matrix as well. So what in the bulk form was a homogeneous mixture, when we introduce the fibers, we start to see issues such as this. So you can see a fiber here, which has a very skeletal structure close to the fiber. So that's good from an ionic conductivity point of view. But remote from the fiber, you can see it's a much denser structure. So that will inhibit movement of the ions. Something else that we've had to wrestle with, which is very different to how things are done in conventional batteries, is the current collector. So this takes the electrons off the electrode and puts them into the rest of your systems. And the conventional approach in which batteries do this is you have a metal foil and then you deposit the electrode onto that foil. But obviously where we're using carbon fibers, we can't use this approach. So we've got to take a completely different approach to our current collection. And what we found is that that current collection and the resistances associated with that is having quite an impact on our scale-up. So when we characterize these devices, we do studies in something called a swage lock cell at a 10 millimeter scale. But we've also looked at an A4 size device, as shown here. And we found that in terms of energy storage, the small scale gives better performance than the large-scale device, and this is down to some resistive losses. But the real problem is associated with how quickly it delivers that energy. At the small scale, we get really good numbers, but as soon as you start to scale up, the resistances within the material become more dominant, and that really penalizes the performance. And this is becoming a sort of a bit of philosophical problem where we're trying to explore what's done in electrochemical devices, where if you look at batteries for a Tesla car, for instance, there are thousands of little A2 size cells within that car. And the approach that electrochemistry takes is to make lots of very small cells. From a mechanical performance point of view, we don't want to have small structures, we want to have large structures which minimize the number of joints. So this is something that we're wrestling with, is how to get around this challenge of the current collection and the penalizing effect that this can have when we try and scale up. Let me move on to the, I'll just run through the evolution of our devices and show you how those have developed over the years. So to put this in context, for a conventional supercapacitor, you have an energy density of about 4.7 watt-hours per kilogram and a power density of about 4.1 watt-hours per kilogram. And that's the cell performance rather than the active material. Our early devices were very simple. They just demonstrated the concept. But you can see we started to adopt different constituents, be more clever in terms of how we developed these devices, and we started to push up the performance. And we started to recognize that there are two manifestations of this concept. You can have a structural device that can carry both fiber and matrix dominated loads. And then you can have a semi-structural device where you use a liquid electrolyte, but you're still using the carbon fibers that have very good membrane properties. So under tension load, for instance, you're getting the benefit of the stiff fibers. So we started to look at semi-structural and structural performance. And the semi-structural will tend to be better because you've got a pure electrolyte in the matrix space. And then where we are now with the fourth generation, and we're just embarking on the fifth generation, you can see that we're getting performance of those devices in the semi-structural state, which is approaching that of a conventional supercapacitor. And even on our structural state, we're getting good numbers for that. And as I'll show you later on, we don't need to achieve the same as a conventional supercapacitor because this is a material that you can also use to make wings or car bodies out of. Let me move on to the modeling work now. And this, I think, is a really important aspect of structural power and multifunctional materials. I think if we don't embark on modeling, then these won't really come to fruition. We're going to need a modeling framework in which to use these materials. So we've done work at the really small scale where we tried to envisage what is the optimum microstructure for the matrix to have the best mechanical and electrochemical properties. So the idea here is that the microstructure of this matrix needs to be rigid enough to allow mechanical load to travel, to be carried, but open enough to allow the ions to flow through the material. So the approach we've been using here has been topology optimization, and we've looked at certain load conditions and flow of the ions, and used topology optimization as a way of coming up with what is the optimum microstructure of the unit cell of the matrix. And that's allowed us to come up with essentially a Pareto front showing for different volume fractions and different weighting of the electrochemical performance and the mechanical performance, what is the front that we get to get that balance. And the way we've tested this has been to 3D print these microstructures that have been generated using the computer and demonstrated them mechanically and electrochemically as well. And this is all published in a paper that came out a couple of years ago that showed this work. And where we've now taken that is we take these microstructures and then we scrutinize what is the local loading stress state within different parts of that structure. And then we can take that library of microstructures and implant that into that structure. So that further optimizes the microstructure of the unit cell. So this is, I think, is a very nice way of starting to explore how to optimize the microstructure for two functions simultaneously. Then moving on to the sort of more conventional modeling side. Now what we're doing here is looking at a strategy whereby we can have modeling tools for structural power materials. And we've recognized very early on the real need to have a way of predicting what is the microstructure during processing. So we've done consolidation models of these devices. So this is showing you the electrodes and the separator as we process the material. Then developing mechanical models, but also within the same modeling toolset, electrochemical models. And I think a really important step here is the need to be able to have interaction between those. So if we start to get damage in our mechanical model, how does that manifest in terms of the electrochemical performance and vice versa? And I think rather than running two different codes, we need to have one code, Abacus, that will be able to run both those models and capture those coupling. And I think once you have that, you have a framework to then start to predict the performance of a multifunctional structure. So just touching briefly on some of that work. So the consolidation work, so there's a paper by Falkova here that covers this work I'm describing here. This is where we developed FE models of the single cell, so the two electrodes and the separator, and started to predict the volume fraction against pressure. And then this allowed us to be able to predict what is the consolidated microstructure. And that becomes important because the distance between those electrodes is going to dictate the electrochemical performance, as well as the local volume fractions and hence stiffness. And then we've taken those models, implanted them into an FE code to start to predict the mechanical performance. But we found that there's a lot of defects generated by the cagging process, by the nature of the electrolyte, that don't occur in conventional composites. And so we found that our models, our pristine models, over-predicted the performance. And so we found that we had to implant defects into those models to start to capture the true mechanical behavior. And we recognize as we start to develop these materials further, we'll eliminate these defects and we'll start to see the benefit of the carbon aerogel on mechanical performance, for instance. And then moving on to the scale up and demonstration of these devices, well, there's a lot of ownership issues that we've started to wrestle with. So how do we scale up? How do we connect to conventional electrical systems? How do we protect from the environment? So obviously those electrodes are electrically charged and we don't want to touch those because they're hazardous. So we need to encapsulate the devices somehow. What's the temperature range they can work out? What is their fire resistance? And again, this is some work that Shoshova's group has done, have looked at the fire resistance of these materials. And then what's their long-term performance? So if you cycle them electrically or mechanically, how do their performance decay over time? And durability, so we've looked at impacting these and whether we get issues that people recognize with batteries. And then finally, the issue of how do we repair and inspect these materials. So over time, we've done a lot of demonstration of this work. We've, first of all, worked with Volvo and made a plenum cover, so that's the bit that goes underneath the windscreen, where we embedded batteries, just to try and understand some of the system issues. And this was very successful. It replaced the start-stop battery that's in the car, and Volvo found they not only got mass savings, they also got volume savings and thermal load savings, because that battery is no longer generating heat in the interior of the engine. So there were benefits we hadn't really thought about. And this drove around Gothenburg for about 18 months, and it rains a lot in Gothenburg as well. So we felt that was a very successful trial. And then we made a boot lid where we took our structural supercapacitors and we built them into the structure, and they carried some of the loading in the structure. And then more recently, we've been looking at aerospace applications. So we've been looking at an emergency door opening system, as illustrated here, such that if there's a heavy landing and the door jams, this electrical system provides the torque which allows the door to be forced open. So this consists in reality on the aircraft as a 4.2 kilogram supercapacitor pack, so there's about 53 supercapacitors there, and a carbon fiber frame. And then what we've been doing is building under the hub work, has been building a C-section beam in which there's structural supercapacitors within there carrying some of the mechanical load. And then we have a demonstrator. So we've almost finished this now, but this is showing you the demonstrator we've made, which is about A3 size. And these are 4 supercapacitor cells. So the video should run. And so essentially, we're just charging the cells at the moment by the little switch at the bottom there. And then disconnect them from the battery pack. And now the switch which Sang is about to press will open and close the door. And this is powered by the structural supercapacitors. And we've shown that we can open and close this door several times before the supercapacitors run out. So it's really just to try and demonstrate how this concept could work. So let me move on to multifunctional design now and talk a bit about the work we've been doing there. So really the motivation for this is, how do we design a multifunctional platform and we compare it to the performance of a conventional equivalent system? So the conventional approach is to put together off-the-shelf devices or structures and assemble those and come up with a minimum mass or a minimum volume. The problem with the structural power material is it's never going to be as good as a conventional structural composite, because it has an added function, and it's never going to have as good electrical chemical performance as, say, a battery, a conventional battery. But that's not really important, because it's actually the combination that it offers which gives you the weight saving. So you have to take a much more holistic view in design of these materials. And so taking a system approach rather than compartmentalized approach is had to be done. And we also recognize this is not one material. We can tailor the balance between electrochemical and mechanical performance to come up with material that has the weighting of those different functions to match the particular requirement. And we developed a methodology that's reported in this paper that explains how we can demonstrate whether a multifunctional material is superior to that of a conventional system. And for our structural supercapacitors, we're just about at break-even at the moment in that stage. So we started to look at how we can use these, and we recognized the aircraft cabin is a really nice place we could start to use these. The idea that you can make the floor panels in the aircraft cabin out of structural supercapacitors or structural batteries and use that to power the seats. So we considered the A320 and did a very detailed study, which is presented in this paper, that shows the electrical systems that we would need for this. We took some targets in terms of the floor panels mechanically and electrochemically, and these are fairly modest targets. This is getting on for where structural batteries are getting to now. And by looking at this concept, we found that you get a weight saving of 260 kilograms per aircraft by going from a conventional system to using structural power in the floor panels. And a lot of this is related to cutting down on the wiring and essentially saving mass and volume in that way. And of course that translates into savings in terms of fuel. We've looked at various other platforms, but let me show you the City Airbus taxi that we've considered. So the concept here is the City Airbus taxi is a 4-seater aircraft which is used for ferrying people across London, for instance. It's a vehicle that exists, and what we did was we considered the scenario of taking out the batteries and replacing the existing structure by structural power material. So that's going to free up cargo space, for instance. So for a given energy density of the storage device, so the black is the what batteries will give you, and this is showing you endurance against specific energy. If you had structural power material that has the same energy density as a battery, you will double the range of the vehicle. So, but if you consider a fixed range, so flying London to Manchester, for instance, conventional batteries would need to have an energy density of about 370 watt-hours per kilogram, which is about 50% higher than conventional batteries at the moment. If using structural power material, you only need to achieve 170 watt-hours per kilogram to be able to get that vehicle to fly from London to Manchester. So again, we're seeing structural power as being a potential enabler for full electrification of aircraft. And of course, that's without considering the savings associated with wiring as well. So let me move on to some of the manufacturing challenges associated with these materials, and generically for multifunctional devices. And these are things we'd not thought about in conventional composites. So firstly, batteries have to be made under a moisture-free environment. The problem here is that if you let moisture into the material of battery during manufacture, that starts to compromise its performance. So we've got to start to think about ways in which we can make not things this big, but aircraft wings in a completely moisture-free environment. Another issue is that we're looking at composites that have multiple matrices. And that in itself is something that is going to be giving us constraints from the manufacturing perspective. And then the processing conditions, when you're imbuing functional properties on a material, those functional properties might be quite sensitive to temperature. They certainly are for energy storage. So the processing temperatures that you use to making your final structure will have to ensure they don't compromise those functional properties. And then there's the issue of secondary processes, drilling and cutting. You can't drill a hole into a battery, for instance. And so these are things that in conventional composites we don't worry about so much, or we've got very mature tools for dealing with. For structural power materials and multifunctional materials, we'll have to think about that again. And then two other aspects, the idea of making curved structures, and the other issue of where you have a structure that has multifunctional regions and monofunctional regions, you want to ensure continuous load transfer across that region. So these last two are something that we've been exploring in the hub. So let me show you, before I go into detail on that, show you how we make our current devices. So the approach is to take the electrode fabric, it's just conventional spread toe fabric, carbon fiber fabric. We infuse that with a precursor of the carbon aerogel, and then we pyrolyze that to produce the carbon aerogel. We add the current collectors, and then we film the matrix onto the separator. So we produce a prepreg of the separator and assemble the carbon fiber separator, carbon fiber laminate. We then consolidate that and then apply more ionic liquid to that to improve its electrochemical properties. And then finally, there's an encapsulation step where we're insulating the layers. So we've been exploring the whole issue of how sensitive these materials are to fabrication. First of all, looking at the different separators. So we could use glass fiber separators or conventional polyethylene separators that are used for conventional batteries, for instance. And we found that some of the separators don't have compatibility with this multi-phase structural electrolyte that we're using. This is the work at Durham. So getting compatibility between the separator and the carbon fiber plies and the electrolyte is very critical. We've also looked at what happens if we vary the content, so the volume fraction of the structural electrolyte. So this is an electrochemical plot. This is showing you energy density against power. And this is showing you for different weight fractions of structural electrolyte. And as you'd expect, the electrochemical performance gets better as you approach the pure ionic liquid form, the monofunctional supercapacitor form. So adding more structural electrolyte reduces the electrochemical performance, but it enhances the mechanical performance. And then something else that we explored, which I think is really important from the point of scale up, is repeatability. So we tried to make nominally identical devices and characterize those electrochemically. And we found that although the energy densities can be fairly similar between those devices, as shown here, we found that very slight variations in the electrical resistance of the devices manifests as large variations in the power. So this again is something that we really need to try and resolve. So returning back to those manufacturing challenges that I spoke about earlier, the idea of we want to make curved laminates, and the way we move forward with that was to introduce fold lines. And this is working with Bristol and Dimitri's group on introducing fold lines on the structure such that we could have regions which are monofunctional and could be used to fold the structure. And then the other regions, the non-folded regions, could be the multifunctional regions. And then looking at this idea of having multifunctional, monofunctional zones, which the load paths were continuous through those. So in conjunction with the group at Bristol, we looked at two ways in which we could address this manufacturing challenge and introduce fold lines. One approach was to produce barriers, such that when you infuse the precursor to the carbon aerogel in, you'll have regions where the carbon aerogel precursor doesn't get to, and those regions therefore don't form aerogel. The other approach is a mask. So the idea is you could use something like PLA, for instance, to mask regions of the structure, infuse the aerogel precursor, pyrolyze that, and then wash away the mask, and you're left with regions where there's no carbon aerogel. So we were very successful working with Bristol on this in producing ways in which we can fold the structure, as shown here. So we've been looking at various challenges associated with developing a C-section beam, looking at having regions where the cap is the supercapacitor as well as the web, and also looking at partitioning the structure, having monofunctional regions, maybe it's a loading pad, for instance, and multifunctional regions. So let me spend a few minutes just talking about the work other work on multifunctional materials that's been undertaken within SimComp. So this is the group at Bristol, Dimitri's group, have been looking at patching and using a way of mitigating for forming defects and allowing us to patch the structure, as I showed you earlier. They've done a lot of work on doing mechanical characterization of these patched regions, and we've adopted this, as I showed you earlier, in producing our multifunctional and monofunctional zones within the structure. But other work has been looking at introducing copper wires or different types of wire within the braid, and then taking that braid and introducing it to a preform, as shown here, and then working in conjunction with that with modeling work to not only predict the architecture of that hybrid braid, but also understand the electrical and the mechanical performance of that. Now, this work has looked at various different materials and tufting patterns and shown to improve the through thickness conductivity quite considerably. And this is very interesting from the structural power perspective, because through thickness conductivity through our electrodes is something that's causing one of those problems associated with the current collection and the scale-up issues. So at Bristol, they've taken this further as a way of looking at sensing damage, first of all in DCB type tests, but then moving that on to looking at more structural elements such as this, and using this as a way of monitoring damage formation within the structure. So I want to now close by just giving you an outlook and some concluding remarks associated with this work. So in terms of where this could be adopted, it's still a relatively immature technology, and it's not going to replace the jet engines on an aircraft for quite a while. So we see it as something that could be used to replace auxiliary power sources. So for instance, relieving the energy that has to be bled off the engines during takeoff in the cabin, just when the aircraft is taking off is when they switch on all the cooking materials in the galley on the aircraft. And by having all localization using structural power material in the cabin would help relieve the load on the engines. From an automotive point of view, we could see we're using it as start-stop batteries, as we've demonstrated. And in aerospace, we're starting to see cabin applications as really where it should be used, because the temperature regime is relatively benign. Other sectors we can see it being used, well, I think electrical bikes, drones. We've done similar studies on drones and found the numbers are very achievable in terms of the energy and power densities we need. And of course, mobile electronics as well. So this is a really exciting area, particularly for transportation, electrification of transportation. Where we are in terms of TRL, I would say structural supercapacitors are about break even in terms of benefit over a conventional system, and they sit about TRL 3 or 4. But there's a lot of things that need to be addressed. As I said, the early adoption routes, But we see this as something that's going to be ubiquitous across engineering. So a paper we've just had published has looked at if you took structural power material and you built a whole aircraft out of that, you no longer need to have hollow wings, and you'd start to see aircraft like this, for instance. And so we've done studies as to if you use structural power in aircraft, these are the implications. And I think this technology is something that's is an enabler to realize fully electric airliners. So from the design point of view, there's new methodologies are needed. And from the manufacturing point of view, as I've said, there's some significant challenges that need to be addressed. I think this is such an exciting idea that you have a material that does two things simultaneously. I think it's something that is going to happen. It's not just a fad. And I think potentially it could have a significant impact, profound impact on all of structural engineering. So just to finish with, something that we are just embarking on is putting together an EPSERT proposal. This is with Bristol and Durham to explore some of these issues associated with manufacture. The idea here is that we've recognized there's a lot of interconnectedness with the electrolyte development, the device fabrication, and the current collection and encapsulation. And so the aim of this project will be to come up with industry-inspired demonstrators that meet these particular targets that I've illustrated here. And so please contact me if you're interested in being involved in this. We're about to submit this proposal, but we're very keen to get industrial interest in this and to sit on the advisory board for this. So to finish then, I just want to acknowledge the funding sources. So I have funding from the Royal Academy of Engineering. I've got a chair in emerging technologies, which allows me to work on this area for the next 9 years it is now. But we also have funding from EPSERC, through the Future Composites Research Manufacturing Hub and the Beyond Structural Project, funding from the US Air Force and from Clean Sky as well. And I just want to thank the organizations that I've listed here that have supported us in our research. Okay, so thank you for your time with that. I'll just unshare the slide now.
Okay, well, thanks for that, Emil. That was brilliant. So there's one question in the question panel. So those of you who haven't, now you have an opportunity to ask a question. So the question that's on the panel, Emil, I don't know if you can see that, but it's thanks for the very nice talk. What about recyclability?
Yeah, well, it is something we've thought about. And I think one of the nice things about having this multi-phase matrix is that it's very conducive to pyrolysis as a way of recycling the material. With conventional matrices, they are a sort of solid phase, and it's quite difficult to extract that. But with this, where we have the ionic liquid, we can wash the ionic liquid out. We're left with a very porous structure. And then processes like pyrolysis will be very quick in terms of taking that material away and recycling it. So it's certainly something we recognise, and we need to do more work on that. But we're quite optimistic about what can be achieved with this.
Yeah, I think you're right, Emil. I think this Steve Pickering and Tom Turner's fluidized bed approach would deal with this very nicely. So Steve and Tom would probably be best to talk to about that. So there's another question from Andrew Reed. Do you think using structural power composites as primary structure in future or casings exposes the item or vehicle to loss of power? Do you think there's a solution to this? How do you make structural power elements replaceable?
Yes, that's another issue is the replaceability of them. One thing that we are concerned about is the temperature regime. So a conventional aircraft, you've got to have structure that can cope with -50 to +100. Conventional batteries can't cope with that, and structural power materials may find that challenging. So at the moment, we're looking at relatively benign temperature ranges. And as we get more confident with adoption of these materials, we will start to explore that. At the moment, I'm not sure how we'd resolve that temperature issue, but it's certainly something we're aware of, I think. And then replacing, yes, again, we haven't looked at repair of these, but it is something that we've been thinking about and dwelling about how we do that.
So there's a question, Emil, about longevity, which I I guess is something similar to how Tesla rate their battery degradation. I guess that's what the question is. Does it degrade with time?
Well, certainly our structural supercapacitors are pretty good. There's no sort of chemical reactions going on with the supercapacitor. You're just moving ions around, and so there's initial degradation after the first cycle, but after that it tends to be quite good. And so from that point of view, it's good. We haven't explored this whole issue of if you damage it, what's that done to the electrochemical performance, but we're trying to dream up tests that we can do that. We can apply mechanical load while we're characterizing the electrochemistry. So I think there's a lot needs to be done in terms of standardization as well. So having tests where you can characterize two functions simultaneously. So I think, yeah, people working on standards have an important role in these materials.
There's a question about crash, particularly automotive structural applications. I imagine they'd be pretty good, you know, because of the fragmentation energy absorption route. Yeah,
potentially. I mean, we've done studies where we've impacted them, where we've penetrated them to try and ensure that they don't, as with conventional batteries, you know, cause a fire and things. And, you know, everyone's seen these videos on YouTube of batteries bursting into flame when you put a nail through them. Because we're using much larger structures, which have much lower energy density than some of these exotic chemistries that are now being used in sort of leading edge batteries, they're much more benign in terms of damage. They just heat up a little bit, but they don't burst into flames. And certainly Natasha's work, where she's been looking at the fire properties, they look superior to conventional composites in terms of their fire properties. So that's quite encouraging, I think.
Yeah. Okay, good. There's a manufacturing machining approach. You know, how might you go about machining this? Well, and Maris is asking, is there anybody on board, you know, an industrial supplier or research team to look into the machining of these materials?
It's something that we'd be very welcome to work with. We have drilled holes in these materials, and I found they're quite benign. But there is this issue of moisture. So if moisture gets into the device, then it could potentially compromise the electrochemical performance. So we certainly think that that's an area that needs to be explored. Yeah, we welcome any interest in taking that forward.
Yeah. And, you know, Matthew has a conceptual question, and because of the cost and the complexity, do you think this will ever move away from high value industries?
I mean, at the moment, I come from an aerospace background, so I've tended to drive it that way. And they're much more driven by weight. I think applications that are not driven by weights, it may be less attractive to those than for transportation. But we've certainly had a lot of interest in the concept from people working in construction. So, for instance, in countries like Spain and Italy, you have solar panels on the roof, and then you have a huge bank of batteries in the basement that store all the energy. But if you could actually make the walls of the building out of a material that stores the energy, it will free up that battery space. So I think from the perspective of volume savings, I think it could be attractive from that perspective. So I think, yeah, in those lower cost areas where you're using a lot more material, I mean, that's quite attractive from my perspective, because if you have a lot of material, then you can store a lot of energy.
Yeah.
And so that, I think there's opportunities in that area.
Okay, cool. Well, it looks like the questions have finished, Emil. I think given the time, it's probably, you know, good. So just for everybody who's logged on, a copy of this webinar will be available on the SimComp website, you know, for anybody to look at that. And of course, if you have any questions, then email them to Alex or myself or Emil directly. You know, we're easy to find on the internet. And you know, thanks for attending to everyone. Thank you, Emil, very much for an outstanding presentation, really interesting. And thanks to Fluency Marketing for hosting this. Okay.
Well, thank you very much for that.
Thanks, Emil. Yeah.